This is Ideas Worth Exploring by Mark MacDonald. Benjamin Franklin was well known as a writer, scientist, inventor, and diplomat, but he was also a huge prankster. Once he made a fake spider that seemed to move by itself when it swung back and forth between two electric wires. He also made a game called Treason, where a portrait of King George was wired up so that it would shock anyone who tried to take his crown. But my favorite of his pranks, which he often did, was to prepare two of his guests by having them rub a glass tube to create static, and then have them kiss each other and get a big electric shock. Let's all aspire to be more like Franklin. Today is the first of a two-part series about two closely related topics, electricity and magnetism. And as per usual, we're going to start by talking about what the ancients knew about electricity and magnetism. There's not a lot to say about magnetism. Some rocks were magnetic rocks stuck to metal, and that's about all they knew. Electricity was a little more interesting. Everybody knows about static electricity. Sometimes you're just sitting there petting your cat, then you get up and touch a doorknob and zap, static shock. What's up with that? Well, the ancients knew at least a little bit about static electricity. We have records of people rubbing a piece of amber with cat fur to produce visible sparks. In fact, the word electric means from amber, where electrum is the Latin word for amber. But static electricity isn't the only thing they knew about. Oh no, I haven't even mentioned fish yet. The electric eel, which is technically a fish and not an eel, is capable of producing an electric shock of up to 600 volts. That's not enough to kill you outright, but it might be enough to paralyze you and cause you to drown. The Greeks and Romans knew about electric eels, and believe it or not, they used their electric shocks to cure headaches. You mock, but there's actually some evidence that electric shocks delivered to facial nerves can be used to treat migraines, so whether or not the electric fish doctors were quacks is not yet completely clear. But, in other news, some types of catfish are also capable of delivering an electric shock, also stingrays, but not jellyfish. Despite what SpongeBob will tell you, jellyfish are venomous but not electric. So, what did people used to think caused electricity and magnetism? You'd think our boy Aristotle would have some answers, but he has surprisingly little to say. He probably knew about static electricity and rubbing cat fur with amber, but none of his surviving works mention it, so we may never know what he thought. As for magnets, Aristotle was surprisingly indifferent to the idea. He kind of went along with an earlier thinker who said that there was a soul in magnets that was attracted to metal. Nowadays, scientists don't generally believe that rocks have souls, though I suppose I can't speak for everyone. But then why does a magnet stick to a piece of iron? The answer is going to come in 4 parts. First, static electricity. Second, electric current. Third, electromagnetism. Fourth, permanent magnets. 1 and 2 will come today, 3 and 4 are in the next episode. This progression will be very helpful, because the concepts build on each other, sorry, I couldn't think of a good joke here. Like a squatter builds on unallocated land, like Pink Floyd builds a wall, like Dr. Frankenstein in a bodybuilding competition. Anyway, the concepts build on each other. Moving on. First, static electricity. If you remember from the episode on the periodic table, I talked about how atoms are made of electrons and protons. If you guessed that electrons have something to do with electricity, you're right. It works like this. There's a thing called electric charge. It comes in 2 types, positive and negative. Over the last couple hundred years, we've observed a rule. 2 objects that have negative charge repel each other. 2 objects that have positive charge repel each other. But one that has a positive charge and one that has a negative charge attract each other. Basically, opposites attract and like charges repel. This is a pretty fundamental observation about the universe we've made, and we need it to understand electricity. When charges are sitting still, then another way to say that is that they're static. The static in static electricity means not moving or at rest. Electrons are negatively charged. Protons are positively charged. But everyday objects, anything large enough to see without a microscope, generally have about the same number of electrons and protons, meaning that the positive and negative charges all balance each other out, and the whole object is uncharged. This happens because the electric force is very strong. My favorite physicist, Richard Feynman, once said that if 2 people stood at arm's length from each other, and each person had 1% more electrons than protons, the force of repulsion between them would be enough to lift a weight equal to the entire Earth. Whoa. But while most of the time you're uncharged, meaning you have equal amounts of positive and negative charge on you, you can change that if you want. Not up to 1%, way less than that, but a little bit. When you rub a balloon against your hair, some of the electrons in the atoms in your hair are grabbed by the rubber in the balloon. This is called the triboelectric effect, and why it happens is still debated. Because of this, your hair gets a positive charge and the balloon gets a negative charge. Your positively charged hairs will repel each other, which causes them to stick up, and the negatively charged balloon will attract positive charges in the wall and let the balloon temporarily stick to the wall. So, static electricity is when charge builds up. Opposite charges attract and negative charges repel. A static shock is what you feel when this built-up charge gets discharged, which just means electrons move from the negatively charged object to the positively charged object to make both objects neutral again. When charge moves like that, it's called an electric current. But before we talk about current, I have to tell you some static electricity jokes. If you buy a sweater that picks up too much static electricity, you can return it to the store and get another one free of charge. Once you manage to get rid of the unelectric charge you've been building up, it should make you feel ecstatic. Finally, after you rub a balloon against your head, you can yell out, "I think I'm electrically charged." And when someone asks, "Are you sure?" you can tell them, "I'm positive." Alright, I just mentioned that moving charge is called an electric current. Not like current events or current jelly, but in the sense of a current of water in a river. Electrons flow like water, and just like water flowing downhill can turn a water wheel, electrons flowing downhill can power a light bulb or heat a toaster. But what is downhill for an electron? It's just what we've talked about before, the opposites attract rule. If a lot of negative charge is built up in one place, then the electrons will want to move away from that place, and if positive charge is built up in a place, then the electrons want to move toward it. A battery builds up negative charge on one side and positive charge on the other using chemical reactions. But if you give the electrons a path to flow through by attaching the ends of the battery together with a wire, then the electrons will flow like water going downhill. This is called an electric circuit. Consider a flashlight, which is just an electric circuit with a light bulb in the middle. As long as the chemical reactions keep happening in the battery, the electrons will keep flowing and your flashlight will keep putting out light. If the chemical reactions in the battery stop, which is what happens when the battery dies, or if the path for the electrons to flow on is broken, which is what happens when you flip the switch on the flashlight, then the current stops and the flashlight stops shining, just like a water wheel stops turning if the water stops flowing. I'm going to abuse the electrons are like water analogy one more time to explain why birds can sit on a power line without getting zapped. Electric current follows the path of least resistance, just like a river. In a river, resistance is caused by physical objects. The water will go around a rock instead of through it. For electric current, resistance is a little more complicated, and I don't want to get into it here. There's some quantum involved. But metal has less resistance than the bird's body. So even though the electricity could travel up the bird's left leg and down the right leg, it doesn't, because the wire has so much less resistance. However, what if the bird touches both the wire and the ground? The electricity would normally have to travel through many miles of wire, then through somebody's toaster, and probably even further before reaching the ground. So if the bird's touching the ground, then the bird's body does have the lower resistance, and the bird becomes the toaster. Fun fact! Silver is the metal that conducts electricity the best, but it's too expensive to use. Number 2 is copper. That's why electric wires are usually made of copper. To further distract you from images of crispy birds, I'm going to talk about someone who didn't get electrocuted, Benjamin Franklin. A slight aside, there's no reason the names negative and positive couldn't be swapped. Physics wouldn't know the difference if we switched the names. But somebody had to decide what to call things, and the man who made that choice was Benjamin Franklin. And he chose wrong. It would make life so much easier for physics students if the charge of an electron was called positive, but no. Now they have to carry around an extra negative sign all the time, and it's all Franklin's fault. But we're stuck with it. So back to Benjamin Franklin not getting electrocuted. Franklin had a hypothesis that lightning was a form of electricity, like a bigger version of a static electric shock, so he did an experiment to test it. Definitely don't try this at home. He first had the idea to shove an iron rod into a storm cloud and see if he could get charge to flow from it. The problem was that Philadelphia was very flat, and he needed high elevation to test his hypothesis. So he was planning on waiting for Christ Church to be built so he could use the steeple for his experiment. But then he had the idea to use a kite instead, with the iron attached to the kite. So Franklin had his son fly a kite through a stormy sky. What a good father, flying a kite with his son and testing a cutting-edge scientific hypothesis in the process, and trying hard not to get electrocuted. A piece of iron was attached to the kite, and the wet kite string conducted electricity down to a key tied at the end of the string. Franklin and his son held onto a piece of silk tied to the string, and they stood in a barn to keep the silk dry so they wouldn't get electrocuted. The iron on the kite became charged from the storm clouds, and the wet string conducted the charge down to the key. When Franklin touched the key, his body gave the charge on the key a path to the ground so that it gave him a small electric shock. Okay, so I lied. He did technically get electrocuted, but only as much as one of those joy buzzers that middle schoolers love so much. Before he took the kite down, he also did an experiment where he charged a Leyden jar, a device used for storing electric charge. This showed convincingly that what was happening in the clouds was really and truly electricity. So really, the term electricity hadn't caught on yet, so he called it electric fire, which sounds so much cooler. So, now that we've hinted at it, let's talk about what causes lightning. Lightning is caused by charges in clouds being separated, with air acting as an insulator so electrons can't flow to restore the balance. It's not completely clear why the charges get separated in clouds, but one theory is that ice falling down and water droplets blown up by the wind rub against each other, and the ice grabs electrons from the water droplets in the same way a balloon grabs electrons when you rub it against your hair. So you get this huge buildup of electric charge, positive charge on top of the cloud and negative charge on the bottom. When the charge in the bottom gets large enough, electrons are stripped from molecules in the air. Air is usually a good insulator, but when its electrons are stripped, we say that the air is ionized, it becomes conductive to electric current. This lets electrons flow from the cloud to the ground or from the cloud to another cloud. First, electrons move as a kind of avalanche, ionizing the air as they go, but the positive charges of the air ions left behind slow down the avalanche. Then more electrons are liberated by the cloud, and the avalanche continues. This start-stop motion is why a lightning bolt looks jagged, like Harry Potter's scar. This electric current can heat up the air it passes through up to 5 times hotter than the surface of the sun. The electric discharge is lightning, and the air heating up so rapidly makes a shock wave that we hear as thunder. Okay, technically you can't see electricity. What you see is when the flowing electrons run into air molecules and excite their electrons, and the air electrons jump back to the ground state and release light. If you didn't follow that, it's a chemistry thing, and more specifically a quantum thing. It's nice when I can call something a quantum thing because then I don't have to explain it any further and you still believe me. But anyway, whenever you see an electric spark in the air, it's because of excited electrons in the air molecules jumping back to their ground state. That means it's impossible to make a visible spark in a vacuum. So, now you know what causes both lightning and thunder. It's electrons moving between the charged clouds and the ground, taking the path of least resistance, as electricity is wont to do. There's a common saying that lightning doesn't strike the same spot twice. That's not true. It strikes the Empire State Building 23 times a year. Lightning will take the path of least resistance, and that usually means striking tall metal buildings, tall wet trees, or tall wet humans. So be careful out there. We live in a world of electricity. Electric lights, electric toothbrushes, computers, cell phones, you name it. Without an electric refrigerator, you would be sad. Electricity has fundamentally changed our society in so many ways that sometimes it's hard to even imagine what life would be like without it. But do we ever stop to think about what's actually happening? While it can be useful to have analogies such as electrons flowing like water to do work, that picture really only scratches the surface. To learn how things really work, you need to be like Ben Franklin and ask a lot of questions, and then try to find the answers to those questions. Oh, what Ben Franklin wouldn't give to have Google. So use your electric computer and make Ben Franklin jealous. And don't forget to come back for the next episode where we build on these ideas about electricity to talk about the wonders of magnetism. Peace. This has been Ideas Worth Exploring by Mark McDonald.